Okay, so I've got this Panasonic MINAS A motor here, which has an 11-wire feedback incremental encoder. There's a serial port on it too, so it must transmit the Hall information over the serial with the index over the serial. There's not much data on this. The inertia, I don't know, I can't find the inertia, but I knew that motor's inertia, so I figure it's half or less than half. So I use my intuition on that. So let's take a quick peek at what we find. Yeah, you can find these motors on eBay, Alibaba. Here's somebody selling them in Taiwan as new, or hopefully it's used, repaired, old, so people dig into the trash can and sell some stuff. That's fine. We can spin it. When you can't find good data for your motor because they don't make the motor anymore, let's take a look at the label on the motor. Okay, so there's the motor model number. I Googled it. That's what I found. Not much. 2.6 amps, 0.04 watts, 200 hertz. Notice the torque constant is on the other side of the motor, 0.13. So the Newton meters per amp in amps RMS, this A stands for amps RMS, is 0.13 divided by 2.6 or 0.05 Newton meters per amps RMS. I convert amps RMS to amps peak, 0.035 Newton meters per amps peak equals KT, the torque constant in volts per radians per second. Convert that to volts per kRPM. I got 3.71 volts per kRPM and I measure 5 ohms. Maybe it's low inductance too, so I don't know, start off with a millihenry and do some current loop tuning. So, given that you have some data for the motor, you can make a speed torque curve. All right, so 2.6 amps RMS times the square root of 2 is 3.67 times 3 is 11, so peak and continuous current. I've got a 24 volt supply, I measured 5 ohms, I got the torque constants in here, and you can go to English for back EMF, but the graph is the same, it just changes the units. But I can hit 6,000 RPM with no load, and then when I have like full continuous load, I get, slowed down. Really, if you want to do full load at full speed, they say the speed is 3,000 RPM, probably going to need more than 24 volts. It said 30 volts AC, three-phase AC, no specified voltage. Huh. All right, well, buy a 48 volt supply. You can go, we can fling the magnets off this thing. Yeah. So I'm going to go through CME configuration here, change settings, brushless, rotary, Panasonic MINAS A. It comes with Halls because they're embedded in the serial. There's incremental count. Oh, I should show the wiring. So where did the wiring picture go? Here it is. All right, so you got your +5 in brown, white and black, shield, not connected to the motor case, but connected at the drive, outer shield, and you got your AA knot, BB knot, XX knot, red, pink, yellow, green, blue, yellow, orange. And then you got your SNS knot for data, light blue and violet. And then I wired it to the drive feedback connector and hooked up the motor power wires in a logical manner, white, black, red, or whatever their phase is, logical manner. 2,500 lines times 4 is counts. You can do some loss detection with index because there's an index marker on the motor, no break. Sinusoidal, you can, buffer output if you want. That's all well and good. I got the data for the motor, calculated these values, measured this. Turns out to be 0.3 millihenry. It's an 8-pole motor. Low inertia, peak and continuous torque. Just multiply the continuous by 3. And crazy 7,000 RPM, which maybe we don't want to go that fast, but we'll see what we can do. What I didn't show in the previous video is the phasing. So we'll just give it an amp because and you can see the red indicator leads the black needle when you go forward, or the red indicator leads the black needle when you go reverse. That's no load. low friction. And if you look at the counts become more positive when you go forward or more negative when you go reverse. You could change the Hall offset if it's not lining up with the Halls. You see there's a wicked lead there and a wicked lag there. That is not balanced. And then you can invert the feedback of the motor. I didn't change anything, so I'm not going to save it. But I do want to show making a move in the system. So this is to verify how fast I can go. So we're gathering the data about a 20 rev move hitting 6,000 RPM with a 24 volt power supply. You see a little blip up there for regen. That's not bad. I'm hitting about 2 amps at this acceleration rate. I do get a voltage limit warning just as I IR drop, but you know, that's okay. A little blip is fine. Just don't be constantly limiting at 7,000 RPM. And then a move and settle. Pretty good setting of the interval gain for the settle. Just going to take it down a notch here. Yeah, that looks pretty good. And, you know, depending on your profile, you might tweak it a bit. It's interesting. It's incremental and not a serial incremental or serial absolute. There's like no following error noise before the move. And then after the move, there's a little bit of buzz, and then gets to 0. So this could be a little, you know, just vibration or whatnot. I don't hear anything. So that's good. Let's go. We can go. Time allows. We can take a look at some tuning. So let's check out the current loop bandwidth. So I tuned this thing up for about 1 kilohertz of current loop bandwidth. So I'm just checking the bandwidth here. You can see nice round numbers tuned by a human. 1.3 kilohertz. If you don't know your inductance, it's going to be hard to calculate. The auto tuning might get you in the ballpark. I tuned it myself. About 1 kilohertz of current loop bandwidth. I tuned up the velocity loop. I had a low gain shift. I unchecked that. It had some like big numbers in here, so I unchecked it, brought them back down to normal values. But when the gain of the velocity loop's too high, you can see it when tuning. So profile velocity, I just lowered the acceleration. Let's look at the auto setup and then hit start. So limited and actual motor velocity. Nice trapezoidal wave. You got a triangle wave, it's going to drift down to one end. Of course, when the gain's too high, it's going to buzz. And I'm not seeing the buzz here, but I'm going to look at the current, actual current. It looks pretty good as far as command and actual velocity goes. But yeah, I remember. I did a 1 hertz low pass filter. So by default, it's gonna buzz. So break it into oscillations, cut the gain in half. You got some gain margin, nice and stable. And of course, if you did a 1 pole velocity, now you can double it again. It's going to get a little noisy and crunchy if you don't have much gain margin here. You see the little ring there. That's at the 200 hertz 1 pole. I'm going to say that's excessive gain, and we'll bring it back down. That would be a better velocity, you know, gain margin and some phase margin. This is no load. So I hook up a load, things are going to look different. You might have like, I don't know, 25 hertz or 100 hertz of velocity filter because of a large inertia mismatch, especially. And then you take the integrator down. But if the inertia is 10 to 1, set PP to 100. If it's 100 to 1, set PP to 10. That will affect the profile again. So we'll take a look at, if somebody might think like, oh yeah, we should have a big integral. Auto setup checkbox. Bunch of revs. And look at the following error. You can't do this. It's you're hitting a voltage limit. The following error shoots up. The integral overshoots and then it settles. So do not over integrate. I guess that's the lesson here, based on the inertia. Well, let me take the velocity down just a little bit. This is kind of doing what the speed torque curve said, right? See, that's normal. No going to the moon spike there, nice and pretty. And then you can look at the current and the voltage and everything, and the voltage limit. Make sure you're not limiting. This has an index, so you can home to it. That's kind of cool. So, motor rotates to the index marker. So we'll monitor the shaft of the motor. Rotates one time, hits the index, backs up, goes to 0, move is done. Or you can move without an adjustment, just go past the index. And then you can set soft limits, but make sure you set a decel rate. And I think that's it. Thanks for watching.